Now let's do a practice problem involving a water pump. So we're given something like this, where we have a pump up there, and the idea is that you're trying to get water from the bottom of that pond up to the top so that you have an elevation change of a total of 12 meters, and then the water flows out the top. So how does it actually work? Well, you have to do work on the system. Water doesn't just pump itself, so let's say that somebody turns that wheel, and sure enough, water pumps out, and then once they stop turning the wheel, suddenly we're not doing work and you run out of water. In real life, of course, this could be an electrical motor, a gas-powered motor, something like that. But in this case, I just had a wheel so you would remember that work had to be done. We're also told in this system that it's a steady pumped flow, so it's a steady state. We're dealing with liquid water, no phase changes, and it's a uniform temperature. Now, we don't know the temperature, but we know that it's the same at the bottom of the pond as it is when the water comes out at the pump. We're also told that it's an insulated system, so we shouldn't expect a whole lot of heat transfer. We're given the inlet density, the inlet radius of the pipe, and the inlet velocity way down there at the bottom of the pond. And we know the exit density. This is water, so you could have written those down. It's roughly 1,000 kilograms per cubic meter no matter what if it's a liquid. The exit radius, and we don't know the exit velocity. That'll be the first thing we'll compute. The second is how much work do we actually need to get that pump running. Remember, when we say work in energy conservation, often we're talking about computing the work power, namely W dot CV. Okay, so let's start with mass conservation to get VE. So m dot I equals m dot E, and we know that we can rewrite m dot as rho A times the velocity for both the inlet and the exit. We know that the two densities are the same, so we can actually just cancel those out, and that tells us that AV, the volumetric flow rate, has to be the same at the inlet and exit. So let's rearrange and solve for V sub E. So that's V sub E, it's velocity because it has years. You can substitute in pi r squared for the areas, and that just tells us that V sub E equals V sub I times the ratio of inlet to exit radii squared. We can put in numbers because we have all that information, so we do that. You may even be able to do this one in your head. The exit velocity will come out to be 4 times the inlet, which is 4 meters per second. That's our exit velocity, and I'm going to write it over there on the left so we don't forget. Okay, so 4 meters per second exit at the pump. Okay, so now we're going to apply energy conservation to figure out the work needed to activate this pump and to run it. So if we go through, which terms are going to be 0? Well, the left-hand side is 0 because it's a steady state. Q dot is 0 because it's insulated. And, we used to be able to cancel out GZ, but we can't do that for a pump. Because in this case, at least, the specific purpose of the water pump is to bring up water to a higher elevation, so Z will change. We'll have to worry about that. So let me simplify with the two terms that were 0, and we want to solve for W dot CV, which is relatively easy. So it's just going to be all this stuff. I substituted in rho I, AI, VI for m dot. We know the inlet conditions. You could just as easily use the exit conditions, and it should come out the same. But we have to keep all that stuff in parentheses, so we need to deal with the specific enthalpies, difference in squared velocities, and the difference in elevation. Let's start with the difference in specific enthalpies. So I'm going to write out little h equals U plus P little v, the definition of specific enthalpy, and we can take the difference in those terms. So HI minus HE becomes the differences in U and PV, getting that sign right in front of the PEVE term. All right. Now we can use a very helpful fact, which is that we're operating at uniform temperature. So the inlet temperature is the same as the exit temperature. That actually implies that the specific internal energies must be the same at the inlet and exit. If you don't remember how this works, you may want to look back at your lecture notes for estimating the specific internal energies for a compressed liquid. You'll recall that you could do that just according to temperature. The pressure didn't matter too much for a compressed liquid. That tells us if we're operating at the same temperature, must have the same specific internal energy. So we can use that to get rid of the little u's, and HI minus HE just becomes the difference in PV. We can rewrite this in terms of the density, remembering that we have the same specific volume at the inlet and exit, so we must have the same density. It's water. So if we do that, the difference in little h becomes the pressure difference divided by rho. Let's substitute that back into our energy conservation expression. So W dot CV becomes all this stuff, but now the specific enthalpy becomes 1 over rho times the pressure difference. We can calculate the pressure difference, so let's do that now. Move that up. What determines the pressure difference between the location of the pump and the bottom of the pond? Well, the pond should be approximately in hydrostatic equilibrium. We are pumping out water, but we're doing so slowly that should not be affecting the pressure at the bottom significantly at all. So actually that means that we can use our usual expression dP dz equals minus rho g. Now we have to be a bit careful using this to make sure that we use the right limits of integration. So on the left-hand side, we'll integrate from the inlet pressure to the exit pressure. That's fine. On the right-hand side, it's minus rho g, where rho is the density of water. And I go from 0 to 10 meters instead of 0 to 12. Above 10 meters, we run out of water. My claim is that the density of air is so low compared to that of water that the air pressure difference between 10 meters and 12 meters is negligible. It's basically the same pressure. That's why your ears do pop when you go 10 meters underwater, but if you change an elevation of 2 meters in air, you don't notice anything. So we'll go through with that calculation, and P minus Pi becomes minus rho g times 10 meters. We'll rearrange it to the same form that's in the energy conservation equation, so Pi minus Pe gets rid of that negative sign, and now we can plug that into our expression for W dot. So W dot is rho, I replace the area with pi r squared, the inlet velocity, times now, so what had been the specific enthalpy term is now 1 over rho times rho g 10 meters. So the rho's will cancel, and we still have the difference in squared velocities and the differences in elevation. Okay, let's plug in numbers. So we do all of this. You knew from the little print that there was going to have to be this really long line, and here it is. Okay, carefully going through, putting in values. We don't really have to be too careful with the units in this case because actually our natural tendency will be to use SI in all of this. We didn't have to look up specific enthalpies that would have been quoted in kilojoules. Alright, so we compute everything, get our signs right. I'll simplify a little bit here and simplify with one more step. So you can check the units and see if we multiply kilograms per second times meters squared per second squared, that ought to give us watts, so that ought to give us units of energy per time, which is watts. And the number we get is that W dot is minus 3405 watts, or if you prefer, minus 3.4 kilowatts. Now remember, if the work power is negative, that implies that we've added energy to the system, which is what you would have expected in this case. Indeed, you have to do work on the pump in order to get it to actually pump water up to a higher elevation, so it all paints a consistent picture.